जनरेशन पटांगम.
පොඩ්ඩක් ඉන්න පොඩ්ඩක් ඉන්න. මගේ ස්ක්‍රීන් පේනවානේ. හෙලෝ
පේනවද?
සරි පේනවා ඇහනවානේ.
ඇහෙනවනේ.
okay okay අපි මුලින්ම කතා okay we are talking about linear algebra. Okay, today we are going to talk about the three main things. One is groups, and the other one is fields, and other one is vector space. Okay, when we look into the groups, so in the groups there is a set. Okay, just imagine a real number with a plus. Okay, there is a real number and plus. So we can add two numbers and get the results, and we can add multiple numbers and get the real numbers. So that's one kind of groups. So when we generalize the groups, so the one thing is there must be one set. Okay, there must be one set, and there is some specific operation. Okay, I put it as a star here. So so in this example, we are looking at real numbers and the addition. So when we generalize it, we can get any number of sets or any space. For example, uh, set. Okay, integers are also set. Sorry, integers are set. So that number of sets and with the multiplication. So that is one type of operation. So if it is a group, there is there is five conditions. So there is five conditions should be satisfied. So the first one is this set should not be null. Okay, there is some elements to do the operations. Okay, so in this real number, there should be some inputs, and we could add something, and we get the outputs. So same thing. So first one is the set doesn't need to be null. Okay, there is some element. There is at least one element. Okay, that is first condition. And second condition is if we perform that function, on the set, it should be a function. So it should be a function. That is second condition. The function means we have to take the inputs from the that set. So we can't get input from other than this set. So if we look into the set as integers, we can't get the half as a input. So input should be in that set. So that is one thing under the function. So if we write correctly, the domain is should be G. So domain means the inputs. Inputs are we should get that from the G, and the output. So output is we call it a range. Range is also in that set. Okay. So the ranges also should be in that set. So for example, if we look at the real number 1 plus 2, so if we add any real numbers, we can get the output as a real number. So that is uh, as a function that should be uh, satisfied. Okay, the first one is domain should be in this that set G, and range is also should be in that same G, and there can't be one to many functions. Okay, in the LLs we study the what are the functions, and so if there is a 1x, so two y values for 1x means that is not a function, right? So the same thing is here. So not one to many relation. Okay, if these three conditions are satisfied, we can call it as a that operations is performing a that is operation is a function on set G. So that is second condition. So we'll look at example and it will be clearly explained to you. And the third condition is uh, third condition is it should be associated. So I think I don't know exactly what the name is. So A star B star C should be equal to A star B star C. So we can't do the operation for three elements in the same time. First, we should perform the operation to two elements and get the result and do it for the third element. So if you as an example, you can use the plus and the real number. So 1 plus 2 plus 3 is equal to, so if we add the 1 and 2 and plus 3, that is always equal to 1 plus 2 plus 3. So it doesn't matter. We are first adding 2 plus 3 or 1 plus 2. So that it means. So this if this condition is satisfied, okay, that is third condition. And the fourth condition is there exists one identity element that is in that set. It should be in that set, and that's for all A in that set. So it should be the two things here. One is identity element should be in the G set, and it should be satisfied for all elements in that set elements of the G. Okay. The condition is um A star is equal to E star A is equal to A. So it means simply 1 plus 0 is equal to 0 plus, sorry, 1 plus A is equal to 0 plus A is equal to A. If you look into the plus and real, okay, the same thing is written in the different form. Okay, the both are same, but the fourth condition is in the generalized form. And the fifth condition is, so this is the last condition for take it as a group. And the fifth condition is there should be inverse. So okay, for all A in the set of G, there exists A. It can be one or two. So at least one, there exists A bar. That is, if we perform that operation with the A, that should give us the identity element. If it gave the identity element, so it is inverse. So these conditions are for groups. If these conditions are satisfied, we can call it as a group. And there is a one more additional condition that is four abelian groups. So four abelian groups
යනුෂාන්
are කියනකම්
මචං මේ උඹේ ස්ක්‍රීන් එක මේ හොරිසොන්ටල් කරන්න බැරිද බං මේ ඔය ටැබ් එක මේ හොරිසොන්ටල් පැත්තට තියලා
horizon හරි මේ පොඩයි දැන් හරිද?
අන්න හරි
හරි.
මේ මොකද බං මේක අර රෙකෝඩින් එක යනකොට මේ මෙහෙම තිබ්බම අර ෆුල් ස්ක්‍රීන් දාගත ඒකයි
හරිද?
හරි බං හරි
Okay. Okay, the sixth condition is for abelian groups. So abelian group is means we can switch the elements. Okay, if the A star B is equal to B star A, if this condition is satisfied, we can tell it as a abelian group. So for example, so 1 plus 2 is equal to 2 plus 1. So it's a one kind of abelian group. So if we look into what are the not abelian, so if we look into the what are the set doesn't get into the abelian group, for example, the matrix. So okay, if we perform matrix multiplication, so it is A matrix, this is B matrix. This doesn't equal as a B matrix into A matrix. So, okay. So these metric multiplications can't be we can't switch the elements between first and second. So if we switch that element, it won't be same. Okay. So this is that metric multiplication can't be get into this abelian group. They can in the general it can't get into the abelian group. So for the addition, we can switch the elements and get the same result. So if we can get the same result, we can call it as a abelian group. Okay. If these 6 conditions are proved, we call it as a abelian group. The first 5 conditions are proved, we can call it as a group. Okay. So we can get into one question. Okay. The question is, it's from the midterm question. So the last year, I'll send the document into the group. Okay. Here, which of the following are groups? So first one is, so if we want to check it is a group or not, we have to check those all 5 conditions one by one. Okay. So first thing, the first thing is the A option is the set of real valued functions that gives we have to give real inputs and the output is real, and the operation is the combination. The operation is combination. So if we f plus g into x is equal to fx plus gx. So this is the operation and the set is real valued function. So real valued functions are the set. Okay, we'll look the is it a group or not one by one. Okay, if we look into the first condition, so the first condition is we have to check it is non-empty. Okay, so real value function. So for example, the f is equal to 1, fx is equal to 1, it's also real value function. So there is at least one element. So I call this set as a f and operation as a plus. So that set f is the set F is non-empty. So first condition is satisfied, and the second condition is we should check it is a function. Okay, this function. So we have to check those three conditions, or um, okay. So we have to check it is a function. So the inputs are in the real value function. So inputs we don't have to think much. So anyways, we have to put the inputs in the set. So we have to think about the outputs. So if we add two functions, okay, f plus gx, it gives us a fx plus gx. These fx and the gx are real valued function. Okay, real value function means if we give input as input one real value x and it gives a real value output. So fx is a real value function, so it output us the one real value, and the gx are also the real value function, and it output as a one real value. So finally, if we add two real numbers, that gives us the real value. Okay, that gives us the real value. The second condition is also satisfied, and for the third condition, it is not. It's not one-to-many relation. So second one is satisfied. Or if your time is very short, you can think about the output only. So if the set is closed, the closed means we getting the output from the sets, or if we are getting the output outside the set. If we get the output as a outside of set, it is not the function. You can think like that also, or you have to check those three conditions, or or if you hurry, you can only think about the output only. The first two conditions are satisfied, and the third condition is there must be exist identity element. So there should be exist identity element from that set, and for all element in that set. So here the identity element is 0. So if we add anything with the 0, so 0 means here function. So it should be a 0 function. So identity element should be a 0 function. So that is equal to 0. So if we add anything with a 0, we get the same result. And the final one is, the fourth one is the exister inverse. Uh, okay, I think I missed one. Sorry, it should be a fourth condition. It should be a fourth condition, and the third condition is it should be associative. I think so. So associative means f plus g plus h into x. It means fx plus gx plus hx. So we can add these both as a first. So fx plus gx plus, so that is equal to hx. We can get the proof, but for the addition, it is associative, right? For the it's also real number, and the three of them are real numbers, so we can shift the brackets. So the third condition is okay, and fourth condition is okay, and the fifth condition is the fifth condition for the group is there should be an inverse. So there exists an inverse in the set G, sorry, in the set F for all elements in the F. Okay, so here the f dash x is equal to minus fx. So if we add the fx plus minus fx, we get the identity element is equal to 0 or 0 function. So this is fifth condition. So the 5 conditions are satisfying with this. So it's a group. So we have to check one by one. So this is one A part. So there is G A B C D G. So I did first one. Okay. So we can conclude first one is a group. Moving to next. So for the B part. So anyways, this abelian group also. So it's addition. So we can switch the elements for the A part. So it's a next one is also same real value function, but with the multiplication operation. So multiplication operation. Here the first part is anyways it's non-empty, and the second part is the multiplication should give g into g results as a g. So we can input the real value function, and when we perform the multiplication, we only get the real value, right? So here f dot gx is equal to fx dot gx. So fx is a real value, gx is a real value. So when we multiply the two real value numbers, we get the output as a real value. So our output is real value. So the second condition is fulfilled. Okay, first condition is fulfilled, and the third condition f dot g dot h is equal to fx dot gx dot hx. So we can it's a multiplication. We can and the three of them are real values, and we can switch the brackets. So fx dot gx is equal to into hx. So we can shift the bracket. Third condition is satisfied. So here the fourth condition is there exists a elementary element for all a in the F. So that is the elementary exists is 1. Okay, one more thing is this elementary element also. So in this identity element is also should be in that same set of G. So same set. If not, it is we can consider it is not a group. So the identity element should be in the same set. Okay. For this one, for fifth condition. So anyways, this B is not a group because the problem is come from the fifth condition. So the fifth condition is there exists a bar in F for all a in the F. Okay, the problem is so if we look into the normal sorry one thing I missed one thing. It's one more thing is B is a set of real value continuous function. It is not a discontinuous function, it's a continuous function. So for the continuous function in example, if x is equal to x squared. So x squared plus 1. So it is one continuous function. So this inverse is we have to perform inverse and the effects. We should get the identity element 1. Okay, for here inverse is 1 over x squared plus 1. For this one, we don't get any problems because this is also a continuous function. This is also continuous. When we look into this function, if x is equal to x minus 2. Okay, if x is equal to x minus 2, it's a one straight line. Okay, but for when we consider this inverse function, so its inverse function is 1 over x minus 2. So when we look into the 1 over x minus 2, it is not continuous. I think graph should be like this. So it is not continuous in the 2. Okay, x is equal to 2 because when we plug into the 2, we get the infinity. So it discontinuous at that point. Okay, so we can say that uh, there are some elements, or there are some elements in the set that does not have the inverse function. So that does not have the inverse. So we can conclude as it's not a group. Okay, this is not a group. We can conclude like that. We'll look only one more example. That is okay. We look into F1. Okay, so real 2 into 2 invertible matrix GL2 with respect to matrix addition. Okay, the F1. Okay, F1. So GL2. So GL2 means it should be invertible. Invertible means its determinant should not be equal 0. So determinant should not be equal to 0. So if that happens, we can find the inverse. And here we are performing matrix addition. Okay. So here also we can check the group conditions one by one. So first one is it's non-empty. The second one is it should be a I'll get the group as a G. When we perform the operation plus in a G set, we have to get the result as a G set. So here G set is invertible 2 into 2 matrix. So here we input as a 2 into 2 matrix. So output, so for example, it is invertible. It's a identity matrix, and here 0 1 1 0. This is also invertible matrix because this is determinant also not equal to 0. So, but when we perform the addition, we get 1 into 1 into, sorry, 1 1 1, this matrix, this 2 into 2 matrix. But this determinant is equal to, this determinant is equal to 0. So that means it won't be, so it is not invertible. So it is not invertible means, so the output is not from that same set. So that means there are some elements we are getting the okay, so we are not getting the elements from the set. Okay, the output is not inside the set of G. The output is the outside of set of G. So we can say it is not closed. So the second condition is not satisfied, and we can say it is not a group. Okay. There are other example also. I'll send the answers. Okay. Uh, and the second thing is fields. Okay. Field is also same kind of thing, but little different. Okay. In the group, we are seeing one set and one operation. But in the field, we are getting one set and with two operations. Uh, kind of so when we so kind of real numbers with the plus and dot. So kind of okay. So we are so though there is a one type of set, sorry, one type of field. Uh, so so field is actually a set having two operations with some conditions. Okay. With some condition, and those conditions are here. There is only four conditions. Okay, there is only four condition. The first one is that if sorry, sorry, we always treat the as a plus and the char as a multiplication. Here, the first one is if set and the first operation should be a Abelian group. Abelian group. If that set is satisfied, we can tell. So, okay, there is four conditions. So this is the first condition, and second condition is if not. So we are subtracting the element from the set. So we are not considering the identity element of sharp. So without that element, the other elements, when we perform the star into other elements, that is a abelian group. So when we look into this real set, so when we perform the multiplication with the zero, if you with the zero, so the fifth condition is every element should have the inverse, right? So the zero doesn't have the inverse. Zero is one over zero. It's infinity, so it is not in that set. So zero doesn't have the inverse. So here also the same reason. So if you perform the star function to the E sharp, we don't get the inverse. That's why we are uh, neglecting E sharp from the F set. So if we perform the other elements to the star function, star operation, it should be a abelian. Okay, the third one is, and the third condition is, if we look into the star, it should be a function. So in the second condition, we neglected the E sharp. For the third condition, we are including the E sharp also, the identity element of sharp also. If we look into the real set, we are including the zero also. If we perform the zero also, we are getting the F as a function. If we perform that operation into F set, F whole set, we get the output inside that same set. Okay, that is third condition. So the fourth one is anyways for this one, for the third condition. For the second condition, anyways, we look E sharp cross. So I'll take it as a G. So G cross G, we got the output as G, right? In the when we check it's a abelian group or not in the group condition, right? When we look into this, anyways, we check for all elements other than the E sharp. For the third condition, when we check for the E sharp with the other elements, that is fine. So here we are checking 0 into the other elements of F. If it gives the same set elements, we can tell uh, it fulfill the third condition. So here in the third condition, we are particularly checking that E sharp thing. We look into the real set, we are checking the zeroth number. So other elements are already checked in the second condition, right? Okay. The fourth condition is so here we look into sharp function alonely and the multiplication function alonely. Here we are looking those both operation simultaneously. Okay, so here for all A, B, C in set F, if we perform A star, B sharp C, we will get the result as A sharp B, sorry, A star B sharp B star C. This is kind of like this. A multiplied by B plus C is equal to A into B plus B into C. Kind of same thing, but in a different symbols. So in the both are giving the same mean. Okay, here we are when we look into the multiplication and the addition, this one. Here we can do any operation, kind of like a differentiation or the function that we look into the previously we look into the function addition, function multiplication, and the matrix addition, matrix multiplication, and we can define the new operation like differentiation order. So we can we can create any operation and we can tell that is sharp and other thing is star. So that's why. So if we put it as a sorry, so if we put it as a multiplication addition, it gives a one thing, right? So that's why to generalize the operation, we putting the sharp and the star. So if these both conditions are satisfied, we can tell that F, the set of F with the sharp and star is a field. If these conditions are satisfied, we can tell this is a field. Uh, here, here also same thing. So in the previous question and this question, give us the the same question, and but in the previous we have to check it's a group. Here we have to check it is a field or not. Okay, shall we do it B? Because we checked uh, the function addition and the function multiplication previously. So if we, so here also we have to check the conditions one by one. Okay, the first one is I have to, so the function is. So I'll define the set as f, and we are performing the plus and the star. They define the plus as f plus g is equal to fx plus gx, and f dot g is equal to fx dot gx, and they said these fg everything are real valued continuous function, so we can't get any discontinuous point in that function. So if we get anything in that inverse or their output, we can tell that condition is not satisfied. Okay, so here first we have to check if and plus is abelian group or not. Okay, already I think we already checked the yeah, here we check the f plus g, so it is non-empty, and it's a function. Sorry, yeah, it's a function. The output is also in this falling into that same set, and the third, fourth, fifth conditions are fulfilling. So, and we can tell uh, if and the plus are abelian group. So we can tell it is abelian group. I'm telling this because of the previous question. And the second one is, so we finished the first operation and the set. So now we have to move on to the second operation. So second operation without the E sharp. So E plus. So previously E plus is equal to 0. We are neglecting 0 and performing the multiplication, the function multiplication. So we should check it's a abelian group or not. Okay. To check this one, yeah, we checked previously. So it's a B part in the first question. So we checked. So it's not only failing to satisfy the fifth condition, that is inverse part. Wait.
ජොන්ෂන්
Yeah, Ken.
ඩිස්ට්‍රිබියුටිලෝ එකේ එර එකක් තියෙනවද කියලා බලන්න පුළුවන්ද? අර කලින්
Which one? The fields in the sit in the field or the groups?
A star B sharp C
A star B sharp C, right? Yeah. Yeah. A star C. Okay. දැන් හරිනේ. දැන් හරිනේ. Hello. Now it's okay, right?
Yes.
Okay. So now we are checking the second one is abelian group or not. So previously we checked it's a group or not. So here the previously is not a group. we checked it is
Yeah, okay.
not a group from question 1. So question 1, so it said it is not a group. So if it is not a group, we can't say it's a field or not. So we can't say it's a field. So so the second condition is not fulfilled. So we can conclude it is not a field. Okay then. And we can we can check the other condition also. So for the other purpose, we can check the other condition also. And the third condition, so anyways, we can conclude it is not a field from the second condition also. Anyways, we'll check the third one also. The third condition is we are defining the star. So sorry, so here it's multiplication. So when we perform the multiplication operation to the set F, we get the output also the F. Here we are inputting, so we are inputting the every condition, sorry, every elements from the set F, and the output is so this is the operation we are performing. Uh, so we are inputting the everything inside, and so it is real value. So it is real value, and it's also real value. And when we multiply the two real value, we always get a real value for all x. So for all x, this means the third condition is satisfied. And the fourth condition is, distributive law. So I h dot f plus gx. So we have to prove h dot f plus h dot g into x. So if that is correct, we can tell it is distributed. The fourth condition is satisfied. So we can write this as a hx into f plus, sorry, hx into fx plus gx. Now it is not a function. So these are real numbers. So hx is real, fx is real, and gx is real. So when we plug the x value, we can get or anyways we get the real value output. So fx and hx are real values. We can now we can distribute them because those are real values. So now we can write like hx into fx plus hx into gx only because those are real numbers. And now we can write this as a h dot f into x plus h dot g of x. So now so it is became to the distributive form. So the fourth condition is okay. Because of the second condition, we conclude this is not a field. So B is not a field. And A is also not a field. We can tell that. So it's a invertible matrix. Invertible matrix plus and the dot. In the previous, the plus is we proved it's not a group. So we can tell it's not a field also. Uh, do I have to do one more question? Sorry.
Kerawan.
Okay. Then I'll do the E1. Okay. The E. Okay. I'll do the part E. Okay. The part E is set of real valued bijective function. So here it's a bijective function. So bijective function means it is one-to-one function and it is on-to function. If the both are satisfied, we can tell it is bijective function. So one-to-one function means there is for one x there is only one y. So it is connected only one. If we so every x there is only one unique y. So there is no two x's for one y. There is only one x for one y. If that is true, that is one-to-one function. And the on-to function means for the codomain, we'll get all the elements as output, all the elements in the y as output. So when we look into the y equal to x plus 2, when we plug the x values, so the y is codomain is also real and the domain is also real. So when we plug the real values, we get the outputs as every real value. So every real value, so we get the every element on the codomain. So every element on the codomain. So this is onto function. This is example for the onto function. So if we get the every elements from the codomain, that is onto function. I don't know what it called in singular. So I think you get it. So if the both are true, we call it as a bijective function. Here we have to check the set of real valued bijective functions with respect to function addition and the composition. Okay, they have two operations. It is a composition. The first one is f plus g into x is equal to fx plus gx, and the second one is fog into x is equal to f of gh. Okay. Here the plus addition and the composition. So we have to check everything. Okay. So those four conditions. So first one is if the set of f and the plus are abelian. So if it is true, we can tell first condition is satisfied. Okay. We'll go one by one. So the f set is non-empty. So first condition is satisfied. And when we perform if inside the set of f, we get the output also f, because here So when we perform the addition in the f into g, so f is also real value bijective function, g is also real value bijective function. So we get the output as a real values. When we add two real values, we also get the real value, and it can be right. So for all x, right? For all x, so we get the output is also a real value bijective function. Wait. So input is okay. The output is, so for all x, f plus gx is equal to fx plus gx. So f is a bijective and g is bijective. So bijective means it means two. It means two things. One is one to one. So there is for one x, there is only one fx. There is only one gx. When we get things, so we can get there is only one unique value, right? So because so fx is unique for that x and gx is unique for that x, so that same x, and when we add those together, we get one unique value, right? Uh, okay, then the output is also in that same set, and the third one is it is not one to many, so it is the second three conditions are okay, then it is a abelian rule. Sorry, the second condition is true, and the third one is associative law. So it's a plus sign, so we can shift the brackets, right? So the third is also right. And the fourth one is there is a identity element. So yeah, identity element is 0. So when we add anything with the 0, we get the same value. And the final one is inverse function. It is inverse function. So inverse for fx is equal to minus fx, right? So when we add the fx and the minus fx, we get the identity element. So we get, so the fx is bijective. Bijective means it is we get the one output for one x. So if we minus that, that is also unique. So for the fx, we get one particular y1. So if we minus the that function, so so the function is considered as a x. So if we minus that function, we get one unique function, right? So unique value. So that is only sign is changed. So this is then we can tell this is also bijective. So 1.5 is fulfilled. 1.5 is fulfilled. We can tell it's a group, but we have to check it's a abelian group or not. So in the addition, we can shift the brackets. Sorry, uh, we can switch things, right? Uh, because of the addition. So because of the addition, we can switch the parts. So if you want to prove it, we can prove it like this. Prove it with the real numbers. So fx is equal to fx plus gx, and fx and gx are real values. So when we plug the x, we get output is real. And for the real values, we can switch things. For the real values, we switch things, and we can write g plus f into, sorry, g plus a x. So and it is commutative. So it is commutative. So 1.6 is okay, and it's a abelian group. So it is abelian group, and we have to check for second condition. Second condition is F without. So here int element is 0. I am neglecting 0, and dot multiplication. It's a we have to check it's a abelian group or not. So here also the first thing is it is non-empty. Second thing is when we perform f, we get the output. The output is also bijective or not. We have to think about that. The first one is so in which we can input the same set function. So first one is okay, and this is output. The output is so sorry. Sorry, here we are not considering the multiplication. Here we are considering the composition. The 2.22 is so f of g x is equal to f of gx, right? So we can write it like this. So it is x, and this is gx, and this is f of g. So this so gx is bijective function, and so we get every element. So every x has one particular output, and the output is output are everything in that set G. So the every element in the set Gx is connected to anyhow some element from the x, and for the f. So f is also bijective function. So from the Gx, it is anyways connected to some element. At least one, sorry, the only one element and to every element. Okay, then we can say that. So here every x are connected to every g, and every g are connected to every f of g. Then we can tell every x are connected to every f of gx. You can tell that, right? Did you get that? So every x are connected to gx, and second thing is every gx are connected to every f of gx, and we can tell that every x are connected to every f of gx. So I'm bypassing this one. Okay, then we can tell that so everything are connected, and everything are uniquely connected. There is only one x for one g. So we can tell that the output is bijective for all x. When we consider one x, we get one particular value f x. So when we look into the every x, we get so if we get the output of the function, we can tell that that is bijective. And here 2.22 is fulfilled, and the third one is also fulfilled. It is not one-to-many relation. And the second condition is okay for the building group. When we look into the 2.3, චරිත් කීයටද ඉවර කරන්න ඕනේ?
එහෙම අවුලක් නැහැ බං. උඹ කරන්න දේ ටික කරලා ඉවරයි නේ.
හරි බං. And when we 2.3, we have to look that it's associative. So F, G, H, of X. So we can write it like, so we have to think, can we shift the brackets or not? So we have to get the final answer like F of G of H. If we get these results, we can tell that it is associated. So we will try to prove F of G of X. So we can write this as F of G of X. So that is equal to F of G of Hx. And now we can I'll write this and explain to you. I'll send the answers for this one. Okay, 2.3. And now 2.4 is there should be one elementary for all in the set. And the elementary here is so here elementary is equal to X. Okay, so elementary element is X because just think about this. I'll take this as a gx function. So gx is equal to X. So if we look into the f of g, we can write this as a f of gx. It gives f of x to us. Okay, we get the same f function as output. So here the identity element is x. Okay, I'll repeat this again. So f of gx, this is a normal operation we are going to do, and f of gx is equal to f of g into x. So gx is equal to x. I put the x as here. So we get the fx as out. So here the identity element is x. So there exists one element for all the elements in the set. And the fifth one is there should be a inverse for every a in f. So for this one, we can tell like, so Inverse is made of when we f of f bar, we get the identity element x. If we get that one, we can tell the f bar uh, is the inverse, right? So we have to find, is there any inverse? So is there any inverse for all the elements in the set of f? The f is a real valued continuous function. For that, we can mm, we can argue like, so f is bijective. So f is bijective. That means there is everything are connected, and everything are uniquely connected. Everything are uniquely connected and connected with every element of output. So we can tell that there should be a inverse. Can argue like there should be one inverse because everything are connected and everything are uniquely connected with the every members in the output. So we can we can tell that so every, so if we input, if we give as an input for some function, for some g function, we can get the every element from the domain. So that function is some unknown function. We can argue like, because it's a bijective. Because it's a bijective, we can argue like for some function, if we input as a the codomain values are inputs, and we can get the x values and unique x values. Uh, so for example, we can tell like if x is equal to x plus 5. So inverse function is, here inverse function is, so inverse function is we have to separate these things. So x is equal to fx minus 5. So when we plug this as a f, so x, it's as a f dash x. So f dash x is equal to x minus 5. So if we input every y values, we can get the every inverse values. So inverse value means the x value. So because it's a bijective, we can argue like that. So we can tell that the every function has inverse function. So mm, so here if we input this one, so if we input, for example, if we input x plus 5 and x minus 5 here, uh, so it's f of f dash x. So fx is equal to x plus 5. For that, we are inputting x minus 5 plus 5. We are getting x. So we can get the identity element. So because it's a bijective function, we can argue like there should be inverse function. So that is, it's also fulfilled. Uh, and other one is the final thing. It's a abelian group or not. So f of gx, and if it is a abelian group, we can write like g of fx. So g of fx means fx. So it's f of gx. And we can say that it is not equal. So when we look at this example as x and the x squared plus, sorry, x plus 1 and the x squared plus 1 is a f, and it's a g. When we plug into these two things, we get different answers. So that's why so if we plug this into here, we get like the final value as x plus 1 whole squared plus 1. If we plug this here, uh, we get x squared plus 2. So these not equal. These both are not equal. So we can say that it is not a abelian group. So it is not a abelian group. Then we can say so second condition is not fulfilled. So we can say it is not a field. So the third and fourth, we can check that. Okay, so it is not a abelian group. So 2.6. So 2.6 is not fulfilled. That's because it's not a abelian group. Because of that, uh, it is not a field. So we have to check one by one. So for every condition. So if the every conditions are fulfilled, we can say it's a field. So if one condition is failed, we can say it is not a field. Uh, I think. And for this question, uh, there is one theorem. Okay, the theorem is the theorem is if and only if f is a field with finite number of elements, the finite number of elements. I mentioned wait, finite number of elements. So finite number of elements uh, n, finite number of elements n. Then so if n is a, if we can write the n as a p of k, and p is a prime, and k is integer. K is integer. So if we can write like this, uh, we can write that set as a field. For example, so the finite element means just imagine f is equal to 0, 1, 2, 3, 4. Okay, 1, 2, 3, 4. So here is a 5 elements. 5 elements. Its operation is mod 5. So mod 5 means if we divide the number with the element with 5. So here I'll do the plus with the mod 5. So we can write the chart like 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So I'm doing the chart for plus thing, and here it's a 0 plus 1, 0, 1, 2. It's not changing. It's changing. 1, 2, 3, 4, and 1 plus 1 is 2, 3, and 1 plus 3 is equal to 4. It's not a problem for here. The problem is coming from 1 plus 4 is equal to 5, but 5 is not in the set. So that's why we are including mod 5. Mod 5 means we are dividing that number with the 5, and we are writing the remainder. Remainder is equal to, here is 0. So it is 0. And here 2 plus 1 is 3. It is 4. And 4 plus 1 is 0. And same 1 plus 4 is 4. And it is 0. And 4 plus 6, so remainder is 1. It is 0 here. 3 plus 3 is 6. So if we divide by 5, the remainder is 1. And here 2, 1, 2, 3. You can fill like this. So kind of, so this is a finite set with the plus operation. So here the number is, so there is 5 elements. So we can write like 5 into 1. So we can write, so we can tell there is a field. There is a field with 5 integer. For example, we can show it like, show this. So this is a field. So if we check all the condition, and when we chart to dot also, we can tell, this is a field for this example. And the thing is, what we can't tell is, if there is a finite element 1, 2, 3, and mod 4, if there is a, this structure is here, and we can't tell because of the structure this is the field. What we can tell is that there is only one direction. So if there is a field with the finite elements, with the n element n, then we can tell the n is equal to p of k. Okay, that should be equal to, n is equal to p of k. Or we can tell, if there is a 4 element, so if there is a some this kind of, we can get this kind of structure for this number of elements, we can obtain at least one field. So we can't define which set and which, what are the operations, and we can't tell that, but what we can tell is there will be a one field, there will exist one field. But what we can't tell is these are the exact field, or if means because of the those element in that some particular set, we can't tell that it is a field. What we can tell is because of that number of elements, there is some field. There can be, we can obtain some field with some operation. Okay, that's what we can tell. So with this theorem, here the first one is, we can't tell, we can't write. So here for this theorem, so we can write the not, right? So if we write the not for this, we can tell it is not a field. So if we count the number of if we can't write number of elements like this, we can tell there can't be field with those elements, right? So we can tell like that. So for the 6 elements, we can't write with the prime and the integer power. So it is there can't be existing one field, and that is for the A part for this. And second is vector space must have at least one element. Um, Vector space must have at least one element. Um, I, it is, I think it is not true because vector space have at least two elements, at least E plus, so E sharp and E star. So vector space must have at least one element. Um, so that is true, right? And the third one is group must have at least one element. That is also correct. And field must have at least two element. Okay. Okay. For the vector space, we haven't covered that. We'll look it later. And there exists a field with the 9 elements. We can write 3 into 3, so 3 into 2, 3 to the power 2. So there exists one field, but we can't say what is the field. So these also we leave that to the later. Okay, next we will go to the vector space. Okay, vector space is so until this we are doing like in the group or the field we are only looking at kind of a dimensional numbers or one dimensional thing. Like we are looking at like real numbers. So in the groups and the fields, that is like 0, 1, 2, and going for the groups and the fields. But here onwards, we are looking at more than one dimension or more than. So like for example, look at like in the A level vectors. So spaces, it is I vector and it is J vector, and these everything are connected with the I vector and the J vector. Okay. So the everything are connected with two things. Okay. And if we repeat like this, okay, then 1 comma 0 and 2 comma 0 kind of like this. So basically it's a vector. So vector means it is not in one dimension or two dimension. So more than two dimension. Sorry, more than one dimension. So in those kind of elements, so we are dealing with those kind of things. Okay, those kind of sets. Okay, for the vector space, so this is a so vector space. We have to define two things. The first one is this one. So I write it like V, and for the vectors we can add two vectors and scalar multiply a vector with one object. Sorry, one set, like in a real number, kind of like. So the vector space is, so I'm doing like sharp and the star. It is vector addition. And it is scalar multiplication. So it is not a vector multiplication, it's a scalar multiplication. Okay. And over, so we have to define, so it is in the scalar multiplication. Now we have to define what are those scalars. So what are those scalars? That's what we need the another field. So over f plus n dot. So this is that scale. So this is that thing. So we are doing scalar multiplication f with b and getting the output. Okay. Those scalar is from a f in this field. This is a field. And the plus and the dot are those operation are for that field, that f, that set of f. Okay, this is for this one. These operations are particularly for this f, and the sharp is for vector addition, and the star is the thing, the connecting the vectors and the field both. Okay. Okay. Now we'll generalize the thing. So there is 7 conditions. So the first condition is V sharp is abelian. Abelian group. So anyways, it's also a set, right? So it's also set, and it is a one operation. So it's a set, it's an operation. We can do the every conditions. We can consider every condition, and if everything's are fulfilled, we can tell it as a abelian group. And the second condition is this thing should be a field. The field. And the third thing is we are defining. Now we are going to define this third thing. So star, this is the scalar multiplication. The scalar multiplication is our one input is from f, from field, and the other input is from the f, and we are getting the vector v as a final output. Kind of remind, do like this. Just imagine like we are multiplying the vector with one number, and finally we are getting output as a one vector. So that is a scalar multiplication. So that is in this condition. Okay, and the fourth condition is so now we have to connect these every operation together. So that is the fourth condition, fifth condition, and the sixth condition. And now the fourth condition is we are connecting the sharp and the star. So kind of a distributive law. So there is three distributive law for here. Now A, so X sharp Y. So it is so A star X sharp Y. So now we can write A star X sharp. So A star, so X is a vector, X and Y is a vector, and A B C A is a scalar. So and if we scalar multiply with A and X, we get the vector. So we have to do it as a vector addition, and the A star Y. This is fourth condition, and the fifth condition is uh, the associative. That's also a kind of associative law with these thing and the star, plus and the star. And the fifth condition is uh, A plus B star X, that is equal to A star X. So here it becomes A star X becomes the vector. So we have to perform vector addition into B star X. Here it is for all A in F and for all X comma Y in V. Here for all A comma B in F, it should be satisfy for every elements in the F and every elements in the P. And the next condition is sixth condition. Now we are going to connect this dot and the star. The dot and the star. It is for all element A comma B in F, comma for all X in V. The condition is A star B star X is equal to A dot B into X. So you can look it like 3 into 5 X vector. So we can write it like a 15X vector, right? So that is what we are writing here. So both for the upper parts also writing here, but to differentiate the vector addition and the scalar multiplication, we use the sharp and the star, and the normal addition and the multiplication, we use the plus and the dot. This is sixth condition, and the final seventh condition is for all X in V, the E dot star X is equal to uh, kind of like 1 into X bar is equal to 1. So it is a identity element of dot. So these both are referring to the same things, but here in the generalized form. So if these conditions are fulfilled, we can tell like it's a vector space over F. So here the most of part is we have to consider third one. Most important is the third one, because the output should be in that same vector space. If not, we can tell it's not a vector space. So if these 7 conditions are fulfilled, we can tell like it is vector space. Uh, um, okay, I'll do this question. Um, so for this question, it's a 4-element thing, and plus and the dots are defined. So I'll do every part. The first one is we have to check it's a field or not. So it's 4 elements, so it's a finite element, so we can easily write the table for the plus and for the dot 0, 1, alpha, alpha plus 1, 0, 1, alpha, alpha plus 1. So here 0 plus 0 is equal to is 0. So here there's a condition x plus x, if we adding the same elements we get the same output, and 1 plus 1 is also 0, alpha plus alpha is 0, alpha 1 plus alpha is equal to 0, and 1 plus 0 is equal to I think others are same. So it's 1 alpha, it's alpha plus 1, 1 alpha, alpha plus 1. So 1 plus alpha is equal to so 1 plus alpha is equal to alpha plus 1. Here 1 plus alpha plus 1 is equal to alpha, right? Because 1 plus 1 is equal to 0, and 0 plus alpha is equal to alpha. So here it's alpha, and it's alpha plus 1. So alpha, so here alpha plus 1 is equal to 1, right? Because it becomes 0. But here it is alpha, and here it is 1. This is plus table, and for the dot 1, 0, 1 alpha, alpha plus 1, 0, 1 alpha, alpha plus 1. For the dot table, they give some condition. 1 dot x is equal to x dot 1 is equal to 1. So identity element is, so u dot is equal to 1. And alpha dot alpha square is equal to alpha dot alpha is equal to 1 plus alpha. Uh, and here also. So these things also. It is 0, 0. Sorry. And 1 it is 0, 0, 0, 0, 0, 0, 0. and 1 into 1 is 1. So alpha squared is equal to alpha plus 1. And alpha plus 1 into alpha plus 1 squared is alpha plus 1 into alpha plus 1 is equal to alpha squared plus alpha plus 1. So it is equal to alpha plus 1. So here there's a condition they gave to us. So plus alpha plus 1, it is 0. Here it is 0. And 1 into alpha is alpha, it's alpha plus 1. So alpha squared is, so 1 into alpha is alpha, and alpha into alpha plus 1 is equal to alpha squared plus 1. So that is alpha plus 1 plus 1, it is equal to alpha. Same like this, it is equal to alpha plus 1. So we fulfill the table and we can tell like, so additive inverse of any element is inverse. So 1 for 1. So here additive element, so identity element is 0. So when we can get the 0? So for 1, it's 1. For alpha, it's alpha. For alpha plus 1, it's alpha plus 1. So first part is correct. And multiplicative inverse of alpha is alpha plus 1. Sorry, sorry. I made one mistake. So alpha into alpha plus 1 is equal to alpha squared plus alpha. So that is equal to alpha plus 1 plus alpha, that is equal to 1. So here it should be 1, and here also. So multiplicative identity is 1. So alpha plus 1 inverse is alpha. So the second one is also correct. And the third one, f cube plus, so plus dot over. So this is, they are saying it is not a vector space. So we have to consider those 7 conditions. If there is one thing is failed, we can tell it is not a vector space. So we'll go through one by one. So we'll go through one by one. So first thing is F3, and the addition is abelian group or not. So first thing is uh, mm, so it's an NMP, and so output is also the same set. And third one is we can shift the brackets. That's also okay. And the fourth one is the inverse. So here 0 is the inverse, and 0 is okay. And the fifth one is every element should have inverse. So that's also okay. And sixth one is we can change it. So 1 plus alpha and alpha plus 1 both are giving same result. So we can 6 also okay. So we can tell it is abelian group. And the second condition is it's a field. So if plus dot is a field. So for this one, so this is abelian group. For the field, this also should be abelian group, right? Okay. For this also should be abelian group. So first we have to so here they are saying it is not a vector space. So if we can do wait. So the third one is it's a field. So the for the field we have four conditions. So it is a abelian group. Yeah, it's a abelian group. And if minus e plus comma dot is a abelian group. So here there is a non-empty and the output is same set. And there is a inverse for everything. There is inverse and inverse for everything. We can shift the bracket also. So the second one is fulfilled. It's also abelian group. It's abelian. And the third condition is for the fields. So the start should be a function. Here we getting the same zeros, right? So it's also the same set. So that is function. So it's a closed. So that is a function. So the final one is associative law. Uh, A dot B plus C is equal to A dot B plus A dot C. That is also true. You can check it. Uh, and so it's a bit. And the third one is so third condition for the vector space is so F and P give the same in the vector space. So here the star is so here we defined as a here they gave us a dot, right? So we have multiplication. So we have to define the scalar multiplication as a dot as F3 and if give the F3. We have to check it is correct or not. So when we get one element from F3 and we multiply with the F, I think same multiplication rule, and anyways we can get the same these four elements. So we'll get these four elements. So we can tell. So there is a proof we have to write, but for the MCQs, we can tell it is closed. And the fourth condition is associative law. This is A dot B plus C is equal to A dot B and B dot C, and this is vector addition, this is scalar multiplication, and there is only two symbols. That's why I'm writing in the one thing. Mm, uh, so so here we have the tables of the plus and dot. Um, mm, um, okay, I'll write these answers and send it to you. And we have to check these everything's correct, is it in the form or not. I'll do one more question and we'll finish. So this thing I'll write the answers and tell it you. And since for the D question is a prime, there must be a deal with co-elements because we look into the previously. So multiplicative inverse is one, and the multiplicative inverse of 1 plus alpha is alpha, that is also true. And with mod 4 addition multiplication is not a field, because if we write the table for this one, I think we get, so it's for the G1, for the G1 is 0, 1, 2, 3, and mod 4. So the addition is there is no problem. 1, 2, 3, 0, 1, 2, 3, and the problem is with the multiplication. 0, 1, 2, 3, and 0, 1, 2, 3. There's a 0, 0, 0, 0, 0, 0, 0. Sorry. The problem is 2 into 2. So 2 into 2 is 4. The 4 means it's 0. 1 into 2 is 2, and 2 into 3 is 6. When we divide 6 by 4, we get 2. And 1, 2, 3, and so the problem is with here. So the thing is, 2 doesn't have a multiplicative inverse. So we can tell the dot is not a abelian group. Then if the dot is abelian group, we can tell F plus and dot is not a field. Not a field. That's why the G is infinite. Okay. Anyways, these have 4 elements, but it's not a field. Okay. mm, okay. Shall we finish it?
ඕකේ කරගත්තට ඉවරයි.
තවත් තියෙනවා හැබැයි ඒකට වෙලා වෙනවා.
අවුලන්න
ආන්සර්ස්
අපි ඊළඟ දවසේ ඉතින් කන්ටිනියු කරමු.
okay. Okay.
Yeah, that
Bye.
concludes.
Bye. Good night.
Good night.